In 1981, a team of astronomers at the Harvard-Smithsonian Center for Astrophysics was doing something that felt completely routine. They were running a redshift survey. The job was simple: point telescopes at sections of sky, collect light from distant galaxies, and measure how fast each galaxy was moving away from us. That velocity tells you how far away it is. You build a map, you repeat. Robert Kirshner led the team. He was methodical, experienced, not the kind of scientist who jumped to conclusions. His team had been working through the data for months, charting galaxies in different directions across the sky, compiling the kind of results that would eventually get published in a journal nobody outside the field would read. Steady work, incremental work. Then they hit a stretch in the data where almost nothing was there. In a segment covering what astronomers measure as roughly 6,000 kilometers per second of redshift velocity, a range that should have contained hundreds of galaxies, they found almost none. The signal just dropped out. It was like running a sonar sweep across the ocean floor and getting back silence where you expected mountains. Kirshner's first thought was instrument error. That is always the first thought. Telescopes have bad nights, calibration drifts, data pipelines have bugs. You assume the machine broke before you assume the universe did something impossible. So the team checked the equipment. They checked the reduction pipeline. They looked for pointing errors, for gaps in the observing schedule, for software glitches. Everything checked out. But they still had 3 separate observation fields, each pointed at a slightly different part of the sky. And all 3 showed the same thing. The same stretch of near-total silence appearing independently across 3 non-overlapping slices of the survey. That is not how instrument error works. If one telescope on one night had a bad run, you get a gap in one field. You get one strange result that you set aside for later review. You do not get the same absence appearing in 3 fields observed at different times, with different telescope settings, processed through independent data pipelines. The fact that all 3 agreed was, in a strange way, more alarming than if only one had shown the anomaly. Kirshner described it in later interviews as deeply unsettling. Not because he thought something was wrong with his instruments, but because the more he checked, the more confident he became that nothing was wrong with his instruments. And that meant the emptiness was real. The team sat with that for a while. A gap in the galaxy distribution this large had never been seen before. The standard expectation was that galaxies, while not evenly spread, would fill space with some reasonable density everywhere you looked. There would be denser regions and sparser regions. There would be clusters and filaments and the occasional relatively empty patch, but a coherent zone of near total absence, hundreds of millions of light years across. That was something the models had not predicted. They published their findings, the scientific community paid attention, and then, slowly, the true scale of what Kirshner's team had found began to come into focus, because what looked like a data anomaly in 3 observation fields was actually the edge of something enormous, something that had been sitting in the universe the entire time, invisible to us until 1981, simply because no one had looked at that stretch of sky with the right instruments. The hole was real, and it was much bigger than anyone thought. To understand why Kirshner's void was so troubling, you need to understand what the universe is supposed to look like. There is a foundational idea in cosmology called the cosmological principle. It states that on large enough scales, the universe looks the same everywhere and in every direction. Homogeneous, isotropic, no special location, no special direction. If you zoom out far enough, any point in the universe is as representative as any other. The universe, at its largest scale, is supposed to be smooth. This is not just a philosophical preference. It is backed by evidence. And the strongest piece of that evidence is the cosmic microwave background radiation. The CMB is the thermal afterglow of the Big Bang. It is light that has been traveling for nearly 14 billion years and is now so stretched by the expansion of space that it has become microwave radiation, filling the sky in every direction. When you measure the temperature of the CMB across the entire sky, it comes out at 2.7 Kelvin, just barely above absolute zero, and it is strikingly uniform. The variation from one part of the sky to another is about 1 part in 100,000 confirmed. That is almost nothing. That level of uniformity is what the cosmological principle predicts, and the CMB delivers it. When cosmologists build their standard models of how the universe evolved from that smooth early state to the structured universe we see today, those models include predictions about how structures can grow. Gravity pulls matter together over time. Filaments form. Galaxies cluster along those filaments. Large, empty regions, voids, develop where matter has drained away into the surrounding walls and nodes. But there are limits to how large those structures can grow in the time the universe has had to work with. The models are fairly precise about this. A void, a region significantly emptier than the cosmic average, should not grow larger than roughly 150 million light-years across, confirmed. That is, the theoretical ceiling. Beyond that size, the physics of structure formation says you simply run out of time. Gravity works slowly on cosmic scales, and the universe is not old enough to have produced emptiness on a much larger scale than that. Think of it this way. Imagine a raisin bread rising in an oven. As the dough expands, the raisins spread out, but they are still distributed throughout the whole loaf. There might be a spot here or there where 2 raisins ended up a bit farther apart, but you would never expect to find one entire half of the loaf with almost no raisins at all. That is what the standard model of cosmology forbids. A void 150 million light-years across is already pushing against the edge of what the models consider plausible. A void significantly larger than that would require either an unusually rare statistical fluctuation, the kind that should almost never happen in the observable universe, or something in our understanding of how the universe evolved that is fundamentally wrong. At this point, in 1981, the Kirshner team did not yet know the full dimensions of what they had found. They knew there was something very wrong in the direction of the constellation Boötis. They had a gap. They had 3 independent confirmations of it, but the actual size of the void would take years of additional observation to establish. And when that size became clear, it crossed the theoretical ceiling by more than a factor of 2. The void in the direction of Boötis has a name now. Astronomers call it the Boötis void, and after decades of careful observation and redshift mapping, we know its dimensions with reasonable confidence. It spans roughly 330 million light-years from one side to the other, confirmed. It sits approximately 700 million light-years from Earth. Let those numbers land for a moment. 330 million light-years means that if you tried to cross this void at the speed of light, it would take you 330 million years just to get from one side to the other. Light from the far edge of this void left before complex life existed on Earth, and across almost all of that span, there is almost nothing. Astronomers expected to find roughly 2,000 galaxies inside a region this size. Theory. They found about 60, confirmed. Galaxy density inside the void is less than 3% of the cosmic average, less than 3%. If you filled a bathtub with the density of matter that exists inside this void, you would have something so close to a perfect vacuum that no laboratory on Earth could replicate it. Here is a way to make the scale personal. If our own Milky Way galaxy were located at the center of the Boötis void, the nearest neighboring galaxy would be so far away that it would have been completely undetectable with any telescope built before the 1980s. Our astronomers would have looked out in every direction and seen only emptiness. They would have grown up believing the universe was just one galaxy surrounded by nothing. The nearest light source outside our own stars would have been beyond the reach of our instruments. But the story gets stranger. The 60 galaxies that do exist inside the void are not scattered randomly. They are not spread throughout the void in whatever sparse arrangement chance would produce. They are strung along a single thin filament that runs through the interior of the void, like a lone wire stretched across an empty room. Confirmed. One thread. One line of galaxies cutting through 330 million light-years of otherwise total absence. This is not what a random distribution looks like. This is a structure, and the structure is deeply weird. The whole picture now looked nothing like what the cosmological principle had predicted. The standard model said the universe would be smooth on large scales. It said structure would be limited in size. It said voids would top out well below the size of the Boötes void, and even the largest would be filled with at least some scatter of galaxies throughout. Instead, here was a region the size of which broke the theoretical ceiling. A region so empty, it violated the predictions of the best models in cosmology. A region with almost no galaxies, and the few galaxies that did exist arranged in a single line, as if something had cleared the room and then draped one string across it. Some scientists tried to argue this could still be consistent with standard models if the statistical improbability was accepted. The odds were low, very low. But in a universe as large as ours, low probability events do occur. Others were not so comfortable with that explanation because this was the first void they had found at this scale. And the universe is very, very large. Those 60 galaxies inside the Boötes void should have been unremarkable. They should have been dim, sparse, slowly fading relics, galaxies stranded in an empty region, quietly burning out. That is the expected picture. A region with almost no matter should produce galaxies that are old, gas-poor, and quiet. Instead, astronomers looked at the spectra of those 60 galaxies and found something that stopped them cold. The light coming from void galaxies showed high excitation emission lines, confirmed. These are the spectral signatures of active, energetic gas. They indicate regions of intense star formation, ionized by powerful ultraviolet radiation from young, massive stars. These galaxies were not quiet. They were alive. Not only that, void galaxies trend bluer than typical galaxies of the same mass. Confirmed. Blue light from a galaxy means it is dominated by young, hot stars. Young stars form when cold gas collapses under gravity. For that to happen at an unusual rate, these galaxies need fresh gas. They need fuel. In a region almost entirely devoid of matter, they somehow have more of what they need to make new stars. This is the exact opposite of what you would predict. Standard galaxy evolution theory says that galaxies in dense environments get their gas stripped away by gravitational interactions with neighbors. They slow their star formation. They age. They redden. Meanwhile, a galaxy stranded in a void, far from any tidal disruption, should process its gas at a calm, slow rate and gradually use up what it has. But the Boötes void galaxies are forming stars at elevated rates. They are blue and active and burning bright. The most convincing explanation is isolation itself. When a galaxy is completely alone, with no neighboring galaxies close enough to disturb it through gravity, its internal gas dynamics operate without interference. The gas flows are cleaner. The collapse of gas into new star-forming regions proceeds more efficiently. There are no tidal forces to strip material away or heat it up. The void is not starving these galaxies. The void is freeing them. That realization flipped something in how astronomers thought about the question. Because if galaxies in isolation are unusually active and efficient, it raises a much harder question about all the other galaxies we spend most of our time studying. The galaxies in clusters, in filaments, in walls, those galaxies are being constantly disrupted by neighbors. They are losing gas to tidal stripping, having their star formation suppressed by the hot gas that fills dense environments, having their shapes distorted by gravitational encounters. Maybe the dense environment galaxies are the stressed ones. Maybe what we study in our surveys and catalogues, those thousands of galaxies packed into the familiar cosmic structures, are the complicated cases, the ones shaped by violence and disruption, and the void galaxies, rare and quiet and startlingly productive, are something closer to what a galaxy looks like when nothing is bothering it. This thought was uncomfortable for a simple reason. Almost all of our galaxy observations come from dense environments, because that is where most galaxies are visible from Earth. If isolation produces galaxies that behave fundamentally differently, we may have been studying a systematically biased sample of the universe's galaxy population for most of the history of the field. The void had revealed a gap in our knowledge as large as the gap in space itself. When astronomers in the 1980s and 1990s began building three-dimensional maps of the galaxy distribution across large volumes of space, they expected something like the raisin bread model. Galaxies sprinkled throughout a more or less uniform distribution, with some clustering and some relatively empty patches, but nothing too extreme. What they actually found looked nothing like that. The universe, at large scales, looks like a sponge, or a web, or foam. It looks like the structure left behind if you inflated a huge mass of soap bubbles and then watched the soap drain to the edges while the interior of each bubble emptied out. There are thin sheets of galaxies called walls. There are long strands called filaments. Where filaments intersect, there are dense knots called nodes or galaxy clusters, the most massive gravitationally bound structures in the universe. And between all of it, there are voids. Not one void, not a few voids. Voids everywhere, vast, roughly spherical regions of near emptiness, each surrounded by the shells and filaments where the matter has piled up. The universe is structured like a cosmic web, and the holes in that web are not the exception. They are the dominant feature. Here is the number that changes everything. Voids occupy more than 80% of the total volume of the observable universe. Confirmed. More than 80%. All the galaxies we have ever observed, all the stars and planets and gas clouds and black holes, and everything else we have ever catalogued or imaged or pointed a telescope at, are crammed into less than 20% of the available space. Think about what that means. The universe is mostly nothing. Not mostly empty space between stars inside galaxies, though that is also true. At the largest scale, the universe is mostly enormous regions where almost no galaxies exist at all. We live in the fraction of the universe that has things in it. But the universe itself is mostly the part that doesn't. This changes the nature of the question entirely. When Kirshner's team first found the Botes void in 1981, the question was specific. Why does this particular void exist? What caused this particular gap? How do we explain this one anomaly in an otherwise normal universe? The cosmic web picture dissolves that framing completely. The Botes void is not an anomaly. It is an extreme example of the dominant structure type in the universe. The question is no longer why this void exists. The question is, what is happening inside all that empty space? 80% of the universe is void. 80% of the volume we can observe has almost no matter in it. And for most of the history of modern cosmology, that vast majority has been treated as background, as the absence between the things we care about, as blank space on the map. What if it is not blank? What if the voids are not passive emptiness but active participants in the evolution of the universe? What if the structures we have been studying, the filaments and walls and clusters, are shaped not just by gravity pulling things together, but by the pressure and flow of whatever is happening in that 80% we mostly ignored? Those questions were speculative in the 1990s. They became more urgent in 2013, when a team of researchers at the University of Hawaii made a discovery that brought the void question uncomfortably close to home. In 2013, 3 astronomers, Ryan Keenan, Amy Barger, and Lennox Cowie, published a paper that reframed the conversation about voids in a deeply personal way. They were studying the distribution of galaxies in a large volume of space around the Milky Way, using a catalogue of infrared selected galaxies to trace the matter distribution across a broad region. What they found was a significant underdensity, a region with noticeably less matter than the cosmic average, extending across a very large volume, and we were sitting near the center of it. The structure they identified is now called the KBC void, after their initials. It is a supervoid, a region of broad, diffuse underdensity, rather than near total emptiness. Its matter density is roughly 20% below the cosmic average, confirmed. That is not as dramatic as the 3% density inside Boötes, but the KBC void makes up for that in scale. It is approximately 2 billion light-years across, confirmed. Let that number sit next to the Boötes void for a moment. Boötes was 330 million light-years and already shattered the theoretical ceiling for void size. The KBC void is 2 billion. It is not a sharp gap in the universe. It is a vast, gentle depression in the cosmic density field, and the Milky Way sits near its center. This has immediate and unsettling consequences for how we understand our observations. Every telescope on Earth, and every telescope we have launched into space, is operating from inside a region of the universe that has 20% less matter than average. That does not sound like much. 20% is not the dramatic 97% deficit of the Boötes void interior, but 20%, applied systematically across every measurement of cosmic expansion we have ever made, can produce a meaningful bias. Here is the mechanism. A void does not simply sit there passively. The matter that should have been inside the void had to go somewhere. It was pulled outward by the gravitational attraction of the denser walls surrounding the void. That outward flow of matter creates what astronomers call a bulk flow, a coherent, large-scale motion of galaxies away from the void center toward the surrounding high-density regions. If you are inside the void, you are inside that outward flow. Every galaxy you observe around you appears to be moving away from you slightly faster than it would if the matter distribution were uniform. That additional velocity gets folded into your measurements of how fast the universe is expanding, and it pushes your calculated expansion rate upward. The Keenan, Barger, and Cowie paper was important, but it did not generate widespread alarm when it was published. A 20% underdensity in a local supervoid seemed manageable. Interesting? Yes. Worth studying? Definitely. But the implications for cosmology were not immediately obvious. Those implications became clearer over the next several years, as a different problem began to emerge at the center of cosmological research. A problem that no one had a clean explanation for. A problem that kept refusing to go away no matter how carefully people checked the data. A problem involving a single number that seemed to have 2 different values depending on how you measured it. The Hubble constant is the number that describes how fast the universe is expanding. More precisely, it describes how much faster a galaxy is moving away from us for every additional unit of distance you add. A galaxy 1 megaparsec away recedes at a certain speed. A galaxy 2 megaparsecs away recedes at twice that speed. The Hubble constant is that rate. It is the fundamental parameter of cosmological expansion. There are 2 main ways to measure it. The first method looks at the early universe. The cosmic microwave background contains tiny fluctuations, patterns in how density varied, in the first few 100,000 years after the Big Bang. The size and spacing of those fluctuations encode information about the physics of the early universe, and by fitting a model to the CMB data, you can calculate what the expansion rate should be today. The Planck satellite collaboration did this with extraordinary precision and arrived at a value of approximately 67 kilometers per second per megaparsec, confirmed. The second method looks at the nearby universe. Astronomers use standard candles, objects whose true brightness is known, to measure distances directly. Cepheid variable stars, which pulsate at a rate that depends on their luminosity, serve as one rung on this distance ladder. Type Ia supernovae, which explode at a consistent brightness, extend the ladder to much greater distances. Teams using this approach have consistently arrived at a value of approximately 73 kilometers per second per megaparsec, confirmed. 67 versus 73. That looks like a small difference. It is not. In science, the significance of a discrepancy is measured not just by the raw gap between two numbers, but by how large that gap is compared to the measurement uncertainty. A discrepancy of 1 sigma might happen by chance 1 time in 3. A discrepancy of 5 sigma happens by chance less than 1 time in a million. The Hubble tension, as this discrepancy is now formally called, sits at 5 to 6 sigma, confirmed. If the standard model of cosmology were correct and both measurements were accurately done, a discrepancy this large would occur by chance, less than once in 3.5 million experiments. This is not a rounding error. This is not a case of two teams using slightly different assumptions. This is a fundamental disagreement between two well-established, independently verified measurements of the same number. The cosmological community spent years looking for the bug. Maybe the CMB analysis had a systematic error. Maybe the distance ladder had a flaw. Maybe the Cepheid calibrations were off. Maybe some local structure was contaminating the supernova measurements. Everyone had their preferred explanation. And everyone was hoping someone else's preferred explanation was the one that turned out to be right. Because if both measurements were clean, then something was wrong with the model that was supposed to connect them. For a while, one explanation seemed especially promising. Cepheid stars in distant galaxies are difficult to resolve individually. In crowded star fields, neighboring stars can blend with the Cepheid signal. This makes the Cepheid appear brighter than it really is, and therefore apparently closer than it really is. If local distance measurements were systematically underestimating distances, the Hubble constant from supernovae would appear artificially high. This was a testable idea, and in December 2021, the tool needed to test it was finally launched. The James Webb Space Telescope launched on December 25, 2021. It was the most expensive scientific instrument ever built at that point. Decades in development, multiple near cancellations, and an engineering challenge so extreme that the mirror had to be folded to fit inside the rocket and unfold in space like a mechanical flower. The telescope operates primarily in infrared light, which lets it see through dust clouds and resolve structures that are blurred or hidden to optical instruments. One of its first major scientific targets was the Cepheid contamination problem. The argument was straightforward. Hubble Space Telescope images of Cepheid stars in distant galaxies were taken in optical wavelengths, where crowding from neighboring stars is a serious problem. Infrared light has a longer wavelength and scatters less, which means Webb could resolve individual Cepheids in galaxies where Hubble saw blurred blobs. If the contamination hypothesis was correct, Webb would find that previous Cepheid brightness measurements were systematically inflated, the true distances would turn out to be larger than estimated, and the local Hubble constant would drop down towards 67, resolving the tension. Astronomer Adam Rees and his team the same group that had pioneered the supernova distance ladder work, deliberately designed their Webb program to test exactly this. They observed Cepheids in multiple galaxies that had also hosted Type Ia supernovae. They measured the Cepheids in infrared with a resolution and precision that had not been possible before. The contamination was real. Webb found it. Neighboring stars were indeed blending with Cepheid signals in Hubble data, and then they corrected for it, and the Hubble constant stayed at 73, confirmed. The 2024 results from this program were unambiguous. After removing the contamination effect that had been the most widely cited potential source of error, the local expansion rate measurement did not change in any meaningful way. The discrepancy with the CMB-based value remained. The tension was not resolved. This was a significant moment in cosmology, and not a comfortable one. The contamination hypothesis had been the most scientifically clean escape route from the Hubble tension. It offered a mundane, instrument-based explanation that did not require any new physics. It was the kind of explanation scientists prefer, because it does not overturn anything fundamental. A calibration error, a known physical effect, a correction that fixes the problem and lets everyone go home. Webb closed that door by providing the most precise infrared measurements of Cepheid stars in the history of astronomy, and showing that the corrected distances still yielded a local Hubble constant of 73. Webb essentially eliminated measurement error as the explanation for the tension. The instruments are not wrong. The data is not contaminated in some uncorrected way. Both measurements, 67 from the CMB and 73 from the local universe, are accurate, and they still disagree by 5 to 6 sigma. The tension is now a confirmed, locked-in problem. Confirmed. It is not a discrepancy waiting to be resolved by better data. It is a discrepancy that better data has confirmed. Something in the standard model of cosmology is wrong. The question is, what? And that question leads directly back to a void, to a specific void, one that a team in Hawaii had identified a decade earlier. The void that our entire civilization and every instrument we have ever pointed at the sky sits inside. Here is the mechanism in full. The KBC void has roughly 20% less matter than the cosmic average. That 20% deficit did not appear from nothing. In the early universe, the region that would become the KBC void had a slight underdensity compared to surrounding regions. Gravity is sensitive to those differences. Over billions of years, the matter that sat inside the void boundary felt a stronger gravitational pull from the denser walls surrounding it than from the emptier interior behind it. Matter flowed outward. The walls got denser, the void got emptier, and the galaxies inside the void, including the Milky Way, were carried along with that outward flow, confirmed. This outward motion is called a bulk flow. It is a coherent, large-scale velocity that all the matter inside the void shares. It points generally outward from the void center toward the surrounding high-density walls. The Milky Way is participating in this bulk flow right now. We are being very slowly carried toward the denser regions at the edge of the KBC void. Here is why that matters for the Hubble constant. When astronomers measure the recession velocity of nearby galaxies to calculate the expansion rate, they are measuring the velocity of galaxies relative to us. But that velocity has two components. One component is the true cosmological expansion of space, the thing the Hubble constant actually describes. The other component is the peculiar velocity, the additional motion due to local gravitational influences, like the bulk flow from the void. If we are inside a void and all nearby matter is moving outward with us, then relative to a hypothetical observer in an average part of the universe, the galaxies we observe around us appear to be moving away faster than pure expansion would predict. That extra velocity looks like a higher expansion rate, the local Hubble constant appears inflated, the math works out in principle. A 20% underdensity in a 2 billion light-year supervoid can produce a bulk flow large enough to nudge the measured Hubble constant upward by several percent. Theory. That could explain part of the gap between 67 and 73, but not all of it. When researchers carefully modeled the expected contribution of the KBC void to the Hubble tension, the numbers did not close the full gap. The void is a real effect. It is a real bias in our measurements. It is almost certainly pushing our local Hubble constant measurement upward, but even after accounting for it, a significant tension remains. The void explains maybe half the discrepancy, maybe a bit more on some calculations, not all of it, which means the KBC void is a piece of the puzzle, an important piece, one that clarifies why our measurements from inside this region are not representative of the universe as a whole. But it is not the whole explanation. Something else is contributing to the tension. Something else is wrong with the standard model, or with our understanding of how the universe is structured, or with both. And just as astronomers were working through the implications of the void hypothesis, they realized they were not dealing with one anomaly. They were dealing with a cluster of anomalies that kept pointing in the same direction. One of those anomalies was not sitting in the galaxy distribution at all. It was sitting in the oldest light in the universe. It was in the CMB itself. The cosmic microwave background is the most important dataset in all of cosmology. It is the thermal afterglow of the Big Bang, a snapshot of the universe at roughly 380,000 years old, when space had cooled enough for electrons and protons to combine into neutral hydrogen, and light was finally free to travel. That light has been traveling for nearly 14 billion years. It has stretched as the universe expanded, cooling from thousands of degrees down to 2.7 Kelvin. Confirmed. 2.7 Kelvin is just barely above absolute zero. It fills the entire sky in every direction. And it is almost perfectly uniform. Almost. There are tiny fluctuations in the CMB temperature across the sky. Regions that are very slightly hotter or very slightly cooler than the average. These fluctuations are at the level of 1 part in 100,000. They represent the small density differences in the early universe that would eventually, over billions of years, grow into galaxies and filaments and voids through the action of gravity. The CMB fluctuations are the seeds of all cosmic structure. Confirmed. Cosmologists study these fluctuations intensely. The pattern of hot and cold spots encodes precise information about the geometry of the universe, the density of matter and dark matter, the speed of expansion, and a long list of other parameters. The CMB is effectively a photograph of the initial conditions of everything, and there is a problem with that photograph. In one region of the sky, in the direction of the constellation Eridanus, the CMB is cold, very cold. The temperature in this region is about 70 microkelvins below the surrounding average. Confirmed. That sounds small, 70 millionths of a degree. But in the context of the CMB, where the expected fluctuations are already tiny to begin with, a 70 microkelvin cold spot is enormous. Statisticians who have analyzed this feature have concluded that it should not exist in standard cosmology. Confirmed. The cold spot is real. It is not an artifact of the measurement. It was first identified in data from the WMAP satellite and independently confirmed by the Planck satellite mission. Confirmed. 2 independent instruments, run by different teams, using different analysis methods, found the same cold spot in the same location. The Planck team's own analysis suggested that a cold spot, this extreme occurring by random chance in the standard cosmological model, has a probability somewhere between 1 in 100 and 1 in several hundred, depending on the statistical method used. Those odds are not impossible, but they are uncomfortable, and they become more uncomfortable when you consider the Boerter's void, the KBC void, the Hubble tension, and the void galaxy anomalies as part of the same picture. Individually, each of these puzzles has some potential explanation. Together, they start to feel like they are pointing at something. Astronomers needed an explanation for the Eridanus cold spot, specifically. And one candidate came from a direction that would have seemed absurd a generation earlier. What if, they asked, the cold spot in the CMB is the imprint left by a supervoid sitting along that line of sight between us and the edge of the observable universe? What if another gap in space is literally casting a shadow on the oldest light in existence? The Eridanus supervoid looked like the answer. It sits almost exactly in the direction of the cold spot. It is roughly 1.8 billion light-years across. That is a real, confirmed, enormous gap in space. And when astronomers ran the physics, there was a mechanism that could actually connect it to the cold spot. The mechanism is called the integrated Sachs-Wolf effect. It sounds technical, but the idea is simple. When a photon of light travels through a region of space that has matter in it, gravity pulls on it slightly as it enters, then gives a gentle pushback as it exits. The two forces balance out, but when a photon crosses through a void, through a region where gravity is nearly absent, something different happens. The void itself is expanding. By the time the photon exits the other side, the void has grown bigger. The photon loses energy during that crossing. It arrives slightly colder than when it entered. So here is what seemed like a clean, satisfying solution. The CMB photons traveling toward Earth from that direction passed straight through the Eridanus supervoid. The void was expanding. The photons bled energy crossing it. They arrived at our detectors slightly colder than photons coming from other directions. That explains the cold spot. Done. Except it was not done. The Dark Energy Survey, one of the most precise, large-scale sky surveys ever constructed, confirmed that the Eridanus supervoid is real. Confirmed. It exists. It is enormous. It really is in the right direction. Nobody disputes this. The void is there. Then came the math. When researchers calculated exactly how much cooling the supervoid should produce through the integrated Sachs-Wolf effect, the numbers came back underwhelming. The supervoid accounts for somewhere between 10 and 20% of the cold spot's temperature deficit. Confirmed. Not most of it. Not half. Not even close to half. 10 to 20%. Which means 80 to 90% of the cold spot's unusual coldness remains attached to nothing. No mechanism, no explanation, just a number floating without a cause. Think about what that means. Scientists found a void 1.8 billion light-years across, one of the largest voids ever measured, pointed directly at the mystery they were trying to solve, and it explained 1/5 of the problem. Maybe less. It is like finding a fracture in a dam wall and then calculating that the fracture is not what is draining the reservoir. Something else is doing most of the work. Something you have not found yet. Something you cannot see from where you are standing. The supervoid is real. The cold spot is real. The supervoid causes some of the cold spot's temperature deficit. Every part of that sentence checks out. And every part of it together still leaves an enormous unsolved gap. Scientists had their answer. It survived scrutiny. It had a known physical mechanism. It pointed in the right direction, literally, and it solved roughly 1/5 of the problem. The supervoid was supposed to close the case. Instead, it became a smaller answer, sitting directly in front of a much bigger question. And now, with the supervoid confirmed and accounted for, there was nowhere left to hide from what remained. That remaining 80 to 90%? Nobody has a confirmed explanation. What astronomers were left with instead were possibilities, and some of them were things nobody really wanted to say out loud. When you eliminate most of the obvious answers, what you are left with is not comfortable. The cold spot had survived every attempt to explain it away. Data confirmed it was real. The supervoid confirmed it was partially caused by something physical, but the majority of the deficit was still sitting there, unmoved, unexplained. Researchers were left with three broad categories of explanation. None of them were proven. All of them carried weight. The first category is the one scientists reach for when they have no better answer: a statistical fluke. The universe is vast. It contains enormous amounts of data. In any dataset big enough, unusual things appear by chance. A patch of sky, this cold, this wide, this precisely placed. Maybe it is just the universe's version of a once-in-a-thousand roll. It could happen. Statistics allows it. But researchers who work with the CMB for years do not find this answer satisfying. The cold spot is unusual at multiple levels simultaneously. Its size is anomalous. Its temperature is anomalous. Its location relative to the supervoid is anomalous. When something is anomalous in three separate ways at once, the fluke explanation starts to feel like a way of avoiding the question rather than answering it. It is possible. It is just unsatisfying. The second category is a primordial origin. This is the idea that the cold spot is not caused by anything that happened recently in cosmic history. It is a scar from the very beginning. In the earliest fractions of a second after the Big Bang, the universe went through a period called inflation. Space expanded at a rate so fast that tiny quantum fluctuations got stretched to enormous sizes. Most of those fluctuations left specific, predictable patterns in the CMB. But some models of inflation allow for unusually cold regions. A cold patch baked into the early universe. Before stars, before galaxies, before anything. A fossil from a moment so early that no instrument alive today could have witnessed it. Theory. This explanation is taken seriously by physicists. It requires no new physics beyond what already exists in the inflationary model. But it has a problem. Nobody has identified a specific inflationary mechanism that produces a cold spot, this cold, this big, in exactly this shape. The third category is the one that makes people in the field go quiet before they answer. It is the category of things that live outside the standard model of cosmology altogether: cosmic textures, topological defects from phase transitions in the early universe, features in the geometry of space itself that current theory does not account for. And in the most extreme corner of this category, something that gets mentioned in careful scientific language with many qualifications attached: a collision in the very early universe with another universe entirely. The idea of a bubble collision, two regions of space existing in a broader multiverse coming into contact before or during inflation, leaves a specific kind of imprint. A cold, roughly circular bruise on the CMB. A shadow from an event so early and so distant that no instrument could ever observe it directly. Unknown. None of these three categories is confirmed. The cold spot sits in the CMB the way a bruise sits on skin. It is real. It is there. It clearly happened. And the cause is still missing. Scientists could not let that stand, so they kept looking. And what they found next had nothing to do with the CMB at all. The CMB was not the only place the universe was misbehaving. While researchers were circling the cold spot, another set of observations was quietly accumulating across sky surveys: deep redshift maps, galaxy catalogs, quasar distributions. The kind of data that tells you not just where things are, but how they are arranged. The arrangement turned out to be a problem. There is a rule built into modern cosmology called the cosmological principle. It says that on the largest scales, the universe is roughly the same everywhere. Smooth, uniform, without any preferred direction or giant clumping. This is not an arbitrary assumption. It is supported by early universe physics. It is embedded in the mathematics of the Standard Model, and it comes with a specific, testable prediction. No structure in the observable universe should be larger than roughly 1.2 billion light-years across. At scales bigger than that, matter should be spread too evenly for anything coherent to have formed. Gravity has not had enough time to organize matter across distances that large. The physics is clear. The limit is well established. In 2021, a graduate student named Alexia Lopez was analyzing data from a major galaxy survey called the Sloan Digital Sky Survey. She was looking at the distribution of galaxies, quasars, and clusters of gas at a specific range of distances from Earth, and in that data, she found something. A curved arc of structures, galaxies, quasars, gas clouds, all arranged along a single sweeping curve stretching across the sky. When she measured it, the arc came out to approximately 3.3 billion light-years in length. 3.3 billion light-years, nearly 3 times the theoretical maximum, a structure that, according to the cosmological principle, should simply not be there. Lopez and her colleagues checked the data. They checked the methods. They looked for instrumental errors, survey biases, any artifact that could produce a false pattern. The arc remained. It became known as the giant arc. When Lopez published the findings, she wrote that the giant arc appeared inconsistent with the standard cosmological model. That is scientific language for something that, in plain terms, means the standard model says this should not exist. It exists anyway. For most astronomers, the first instinct when confronted with a structure this anomalous is skepticism. Patterns can emerge from noise. Human eyes are wired to find shapes. Survey methods can introduce clustering artifacts. So the giant arc was treated carefully. It was noted, scrutinized, and debated. But here is what makes it difficult to dismiss. It was not found by someone searching for something unusual. Lopez was doing systematic analysis of a known dataset. The arc was not hidden or subtle. It was sitting in the data, stretching across a region of sky that multiple surveys had already mapped. Large structures had been found before, but nothing at this scale. Nothing nearly 3 times larger than the model said was possible. One anomaly is a data point. You can set it aside and keep working. But anomalies have a way of inviting company. And in 2024, from the same region of sky, Alexia Lopez found something else entirely. The same region of sky, the same researcher, 3 years later, a different shape entirely. In 2024, Alexia Lopez was again working with data from the same survey region where she had found the giant arc. This time, she was not looking at a linear or curved structure. What appeared in the data was a ring. The Big Ring, as it was named, spans approximately 1.3 billion light-years in diameter. To put that in perspective, the distance from Earth to the nearest neighboring large galaxy, Andromeda, is about 2.5 million light-years. The Big Ring's diameter is more than 500 times that distance. But size alone is not what makes the Big Ring so strange. Massive structures exist in the universe. Filaments, walls, clusters. Size is not automatically impossible. What is almost impossible is the shape. The Big Ring is almost perfectly circular. Not roughly circular, not approximately ring-like. Almost perfectly circular, like a hoop drawn in space, made of galaxies and gas, sitting at a specific distance from Earth. Natural processes do not produce perfect rings at this scale. The universe does not draw circles. Gravity forms filaments and walls and sheets. It does not spontaneously arrange billions of solar masses into a clean geometric hoop. There is no known mechanism in the standard model that would create a structure shaped like this at this size. There is one process that does produce ring-like structures in the universe. It is called baryon acoustic oscillations. In the early universe, before atoms even existed, sound waves rippled through the hot plasma of the Big Bang. When the universe cooled and atoms formed, those waves froze into space. They left behind faint rings of slightly higher matter density that still show up in galaxy surveys today. Those rings are real. They have been measured many times. They are a cornerstone of modern cosmology. But the rings left by baryon acoustic oscillations are about 490 million light-years in diameter. The Big Ring is 1.3 billion light-years in diameter. That is nearly 3 times too large. And the geometry is also wrong. The frozen sound wave rings have a specific 3-dimensional shell shape. The Big Ring looks more like a flat hoop. The two structures are not the same kind of thing. So baryon acoustic oscillations cannot explain the Big Ring, and nothing else in the standard model can explain it either. Now consider what Lopez had found within 3 years of each other in the same patch of sky, the giant arc, stretching 3.3 billion light-years. The Big Ring, spanning 1.3 billion light-years in almost perfect circular geometry. 2 structures, both in the same region, both violating the theoretical maximum size, both without a confirmed explanation. Lopez presented both findings together at an American Astronomical Society meeting. She noted that the probability of 2 such structures appearing by chance in the same survey region was extremely low. She was careful with her language. She did not claim the model was wrong. She said the data was inconsistent with it. The field paid attention, but the debate was only just beginning. Because while Lopez was mapping these structures at distances measured in billions of light-years, there was another structure already in the record books, one so large it makes the giant arc look small. There is a structure in the universe called the Hercules Corona Borealis Great Wall. It was announced in 2013 and confirmed through additional observations in the years that followed. It is detected not by mapping individual galaxies directly, but by tracking the spatial distribution of gamma-ray bursts. These are the most energetic explosions known in the universe. They occur when massive dying stars collapse or when neutron stars collide. They release more energy in a fraction of a second than most stars release across their entire lifetimes, and they are visible from almost anywhere in the observable universe. When researchers looked at where gamma-ray bursts were clustering in space, they found a region where the concentration was far too high to be chance. That region of concentrated gamma-ray bursts traces out a structure approximately 10 billion light-years across. 10 billion light-years. Let that sit for a moment. The observable universe is about 93 billion light-years in diameter. The Hercules Corona Borealis Great Wall occupies roughly 1/10 of that, one single structure, in one region of the sky, 10 billion light-years from one edge to the other. Light travels at 186,000 miles per second. That is the fastest anything in the universe can move. At that speed, crossing the Hercules Corona Borealis Great Wall would take 10 billion years. The universe itself is only 13.8 billion years old, which means light traveling at maximum speed since shortly after the Big Bang has not had enough time to cross this structure end to end. The cosmological principle says no structure should exceed 1.2 billion light-years. The Hercules Corona Borealis Great Wall is more than 8 times that size, not slightly over the limit, not marginally over the limit, more than 8 times past it. For this structure to exist, matter would have had to organize itself across a distance so vast that the known forces of gravity, working across the entire age of the universe, cannot account for it. There has not been enough time. There has not been enough gravity. There is no known mechanism that produces anything at this scale, unknown, awaiting confirmation from independent datasets. Now consider the full picture together. The cosmological principle sets a hard limit, 1.2 billion light-years. That limit comes from detailed calculations of how matter has behaved across cosmic time. It is built into the core mathematics of the Standard Model. The giant arc exceeds it by a factor of 2.75. The Big Ring sits right at the boundary, with a circular geometry that should not exist. The Hercules Corona Borealis Great Wall exceeds the limit by a factor of more than 8. 3 structures, all in the observational record, all violating the same fundamental limit. One of them by a factor that is not close, not marginally inconsistent, more than 8 times the permitted size. And the cosmological principle is not a footnote. It is not a side assumption. It is the foundation the entire Standard Model of cosmology is built upon.